Alright, let's look at some examples using the principle of conservation of energy. So we're going to go through 3 different examples. And some of them are a little easier, some of them are a little bit harder. But let's look at what we got going on here. So we got a human cannonball in the circus. They are shot at a speed of 21 meters per second at an angle of 20 degrees above the horizontal from a platform that is 15 meters above the ground. So the acrobat has a mass of 56 kilograms. We want to find the gravitational potential energy relative to the ground when he's at his highest point in the flight. Ignore the effects of air resistance. Right, let's have a look at what we have going on here. So, I have this person. Here is the ground. So, we're told that they are being shot at a speed of 21 meters per second. And it's happening at an angle of 20 degrees above the horizontal. And we happen to know that this platform is 15 meters above the ground. So we'd like to know what is the gravitational potential energy at the highest point. So here's what we got going on. So at the highest point, let's look at this. We can look at the mechanical energy. We know that the mechanical energy at some point A is going to equal to the total mechanical energy at some point B. So point A is going to be what we're going to call this our launch point. B is going to be at max height. So how I could rewrite this, I could say that the kinetic plus the potential at the launch point, it's equal to the kinetic plus the potential at the maximum height. So what we are interested in finding is this potential at maximum height. Now, we are told we have to find it relative to the ground, so we have to take our measurements relative to the bottom here. That is just how it's going to work. We can't change the reference point if the question says to do it this way. So we know that the potential energy at the maximum height, it's going to be the kinetic plus the potential at the launch point, and then we have to subtract off this contribution of the kinetic energy at the maximum height. So these things we know. We know kinetic energy is just half mv squared. We know that the potential is just going to be mgh. And then we're going to take this half mv squared. So I have my masses, which is good. I have my speed at launch. I have my height at launch. Now, this is where we're going to try and trap you. So we might say maximum height. People are going to say, oh, speed 0. But remember, this is a projectile. So the Vx does not change. Vy is certainly going to be 0. So that's where we're actually trying to get you. So I want to put this on the side. So for projectiles at max height, and this is the trap on this one. So for projectiles at max height, Vx is still going to be a constant, which is not going to be equal to 0. But Vy at max height is going to be 0 because the projectile is still moving horizontally. Just at maximum height, the y it's not moving vertically at that maximum height. But we do have to find what Vx is. So Vx is going to be our initial speed multiplied by cos of our angle. So we got our initial speed. We're told it's 21 meters per second. And then we have cos of 20 degrees. So this is going to give us the x component of our projectile's velocity. So this is going to give us about 19.734 meters per second. The key is that this does not change. So this does not change during the flight. What that means is at the maximum height, this v at maximum height is going to be this Vx. Now, the other thing before we plug in things, people might say, well, for VA, it's 21 meters per second at 20 degrees above the horizontal. What do I do with components? Here's the great thing. Energy being a scalar doesn't care about components, direction, any of that. You just have to put in the magnitude, the end. That is one of the reasons why we like to use conservation of energy. It cuts down a lot of the vector stuff. We did have to do a little bit here to find this Vx component, but that's it. You don't have to worry about vectors and directions with energy. It is a scalar quantity. So let's find this potential energy. So we got half the cannonball, this mass, 56 kilos. We have that 21 meters per second. We have that 56 kilos. We have our 9.81 meters per second squared. So our height above the ground at this point is 15 meters. And then we're going to subtract off that piece for the kinetic energy. So again, want to make sure we account for that speed there. So that's our Vx at max height. So we have a lot of numbers to crunch in here. So let's see what we got. So we got 0.5, 56 times 21 squared, plus 56 times 9.81 times 15 minus, oh yeah, a lot of places to make mistakes here. So you gotta be really careful with that. So what I'm gonna find is if I'm really careful with this, we're gonna find that the potential energy at this point is about 9.86 times 10 to the 3 joules. So at the maximum height, relative, and this is important, this is relative to the ground, the potential energy of my cannonball, it's going to be about 9.68 times 10 to the 3 joules. So the next part, so the net that this person's going to land in, it's 2 meters above the ground. We want to find out how fast he's traveling when he hits it. So this is where we're going to start to show you how we can simplify the problem a little bit. So let's look at this. So again, I'm going to draw my little sketch here. So here's the person. Here is their trajectory. So here is their lovely little net that they're going to jump in. So they're going to do something like this. And yeah, they're just going to barely hit the net in my case. So we still know that this is 15 meters above the ground. We're also told that the net, it's 2 meters above the ground. Now, at this point, the great thing with the conservation of energy is that you can pick the 2 points where you'd like to examine mechanical energy. So I could pick I have to include the net because I want to find the speed there, but I could also use the maximum height. I could also use the launch point. I would say use the launch point just because we know the information there already. We had to calculate stuff at max height. So what we could say is that the mechanical energy at some point A is going to be equal to the mechanical energy at some point B. So at this point, A is going to represent our launch. B is going to represent the net. Now, let's start to expand this out. So I could say that the kinetic energy at A plus the potential at A is equal to the kinetic at B plus the potential at B. Or, we could start to... Now, actually, I will simplify that in a little bit. You could take all of your measurements relative to the ground. That's fine. But in this part of the question, we haven't really told you where anything is defined from. You are free to set your own reference point. And this is a really nice thing in conservation of energy because this helps us simplify problems. What if I don't want to use the ground as a reference point? That seems pointless to me. What if I want to call the top of the net here? What if I want to call that my reference point of h equals 0? There's absolutely nothing wrong with that. And in fact, that's what we're going to do. We're going to say, well, the top of this net, that's where I'm going to make all my measurements from. So I'm going to call this height equals 0, which tells me that my launch point, instead of being 15 meters above the ground, it's going to be 13 meters above my launch point. And we got to be really careful. If you're going to set a new reference point, make sure that your measurements correspond to that. Why would we do that though? Well, the reference point where I set the height equals to 0, what that also allows us to do at that point is that allows us to set the gravitational potential energy at 0. So EPB, this potential energy at the net, with our choice of reference, we're going to set that to 0. That is why we do that. It makes life a lot easier for us. So let's expand out these terms. So we got half mv at the launch squared plus mg, the height of the launch relative to this new reference point, or 13 meters. And then we have this half mvb squared. So what I'm interested in is in finding the speed when this thing hits the net. Here's where we can simplify though. I have a mass term here, I have a mass term here, and I have a mass term here. I have mass in all three of these. I can cancel out mass. So what I'm left with is this half VA squared plus GHA is equal to half VB squared. So this simplified quite nicely. I don't want the half here, so I'm going to multiply everything by 2. Remember that when you're multiplying or dividing, every term is multiplied or divided by the same thing, so we have to multiply every single term by 2. So this half and 2 are going to get rid of each other. That half and 2 are going to get rid of each other. And then 2 times GHA is just going to be this 2GHA equals VB squared. So what I can now write is I can say VB is going to be the square root of this VA squared plus 2GHA. So this will allow me to find my speed based on the information I have. So I have this 21 meters per second plus this 2 times 9.81 meters per second squared. And again, with conservation of energy, you're not using any negatives here. We are just using magnitude. So this will be positive 9.81 no matter what. And then our height of the launch point relative to our new reference is 13 meters. So make sure you're careful with that. So again, a lot of work going on here, a lot of places to make mistakes. Take these questions really slow and methodically. And yeah, we'll get about 26.4 meters per second. So this allowed us to find the speed without doing all the projectile motion equations, which is nice. The disadvantage is we can't find the angle without going through some of the labor work, which is a little unfortunate, but it is what it is. Like, you know, there's always going to be drawbacks to our little shortcuts. So using conservation of energy, we found that the speed when this person hits the net's 26.4 meters per second. If you had used the ground as a reference point, you would still get the same answer. That's the joy. Regardless of the reference point you set, we may have some different numbers in our intermediate steps, but we will all agree on the same answer, which is a good, powerful thing about this tool.